So in the last lecture, we explained what variational quantum algorithms are, and there is a particular family of variational quantum algorithms that are called variational quantum eigensolvers. Okay, so basically, a variational quantum eigensolver is any variational quantum algorithm whose goal is computing a ground state. Actually, indeed, in the example that I gave yesterday, the cost function was the expectation value of Hamiltonian. We could say that this would be an example of a variational quantum eigensolver. So today, in today's session, we will present a particular case of a variational quantum eigensolver, which is the quantum approximate optimization algorithm, QAOA. So then, yesterday we saw what variational quantum algorithms are. We indeed presented a cost function corresponding to a variational quantum eigensolver, whose goal is to find the ground state of a Hamiltonian. And today we will present the most popular example of variational quantum eigensolver, which is this QAOA. Let's look at how the answers of the QAOA look like. How does the ansatz of the QAOA algorithm look like? So basically what we see here is that we start with a product state of zeros. Then we apply a series of single qubit gates that are Kalman gates. So after this state, the state system here is a superposition of all the elements of the computational basis. Okay. Then we start to apply a series of layers, T layers, where every layer consists of two unitaries. Okay? One first unitary called UP, that is defined here as the time evolution of the Hamiltonian HP, that now I will explain what it is. And a second layer that is the time evolution under a different Hamiltonian H0. Okay? Notice that here in the last layer, the layer number P, I only have represented the second unitary, and this is in order to save space, to have more space to work right everything in the blackboard. Okay, so what are the Hamiltonians HP and H0 that define these unitaries? So the Hamiltonian HP is a Hamiltonian that depends on the problem. Okay, so remember that we are trying to solve an optimization problem, right? So our problem, the problem was the goal of the optimization problem was to minimize some classical function that was depending on bit strings. No, we wanted to find a bit string that minimizes this function f. Okay. In order to do this, what we did was we mapped this. Okay, in our case, this function was a QAOA, and then could be mapped to an Ising Hamiltonian. So this Ising Hamiltonian is precisely our HP. Okay, it's the Ising Hamiltonian that we have written already many times in this course. Enough space, and this will be the HB Hamiltonian, the problem Hamiltonian. Okay, good. So notice that this Hamiltonian depends on the problem. So the ansatz of QAOA depends on the problem that we want to solve. So on the function we want to solve, that implies a different Ising Hamiltonian. Okay. Unlike the problem Hamiltonian, this H0 Hamiltonian is problem independent, so it's always the same Hamiltonian. And actually, is given by this mixed Hamiltonian. That this should remind you to the Hamiltonian that we have in the adiabatic quantum computation, where we are doing an interpolation between this H0 and this HP. In the second part of this lecture, we will show the connection between the QAOA and the adaptive quantum computation. And we will see that the fact that these Hamiltonians are the same is not by chance, but it has a reason. Okay? Good. One other comment is that notice that although I have written here the U not unitary as a whole box, because of this Hamiltonian being non-interactive, this box will be computed as a just single qubit operation. Okay. Good. It's important that we don't forget that this is a variational quantum algorithm. That is, that all these parameters that we have, p gamma parameters and p beta parameters, so in total 2 p parameters, these are the parameters that need to be minimized in the variational quantum algorithm. So here, I just, in order to make things simpler, I then put explicit the measurement part, the classical optimizer, and the flux of proposing new parameters in order to iterate this process that we were explaining yesterday of the variational quantum algorithms in order to reach the minimum of the energy. Okay? So I think that with this we have explained the main important elements of the quantum approximate optimization algorithms. So now I would like to mention what is the performance of this algorithm. So the performance is a bit heuristic, so we have no clear proofs that when this works. So we know some things. So we know that the algorithm is universal. And this universality may require an infinite amount of layers. So universal means that it can reach any state. So it can reach any ground state of any of these apparent Hamiltonians. But in some cases, it will require infinite layers. So infinitely many recesses. Okay, but this is one comment that is important. In practice, we have seen that with few layers, you can achieve good results of, I don't know, for instance, problems like the max-cut problem. The max-cut problem for, I don't know, like graphs of 3 regular and etc. So the more complicated the problem, so instead of 3 regular, we have 5 regular. What we notice is that to get a good performance, what we need to do is to add more layers. Okay? Basically, there are numerical evidences that the irregular graphs can be, for the max cut, can be very well approximated with QAOA. In general, we don't have rigorous results. Okay, so it's a bit of heuristics, and we should try when it works and when it doesn't. Okay, so remember that typically the manifestation of that the QA is not working will come from the optimizer. From the classical optimizer is not being able to find the global optimum. Okay. Next thing I want to comment is that there are some variants of this quantum approximation algorithm. And the variants basically consist of different initializations. Okay, so maybe we can call this part here the initialization. So basically, this part here prepares an initial state psi 0 on which we apply this sequence of unitaries, right? So the variants of the QAOA basically consist of putting here different initial blocks. Okay, So one common block is what people call warm starts, and is that instead of starting for this uniform superposition of all possible states, we start with certain states that are close to the minimum. If we have some hint about what's the minimum, we could start with the state already here. Okay. Also, in our group at Kilimanjaro, we proposed a star that was initialized in this QAOA instead of with this, if you want, completely uniform state, initializing the algorithm with pure eigenstates that are states that, let's say, given an energy that you try to start with an energy as small as possible, you maximize the entropy, the coherence and entropy. We have seen that these states improve the performance of QA. Okay. So what we're going to do next is that show the connection between the QAOA and the adiabatic quantum computation. So now I would like to convince you that the adiabatic quantum computation is a particular case of the QAOA. Okay? So in order to do that, let's remember how the adiabatic quantum computation was, right? So basically, the final state was the result of making the time evolution of an initial state. That remember that this initial state this initial state was the uniform superposition of all the elements of the computation basis. Okay? Then we were doing a time evolution very slow, where we were interpolating between two Hamiltonians. So this Hamiltonian H of S was basically 1 minus S H naught plus S H P, where H naught and HP are the ones that we have just seen 2 minutes ago. Okay, so basically what I would like to do now is just show you that if I massage a little bit this expression, what we see is that indeed, this state here, it can be seen as a product of unitaries, of a commutation of unitaries, UP and U naught that we have seen before, for some values, certain values of beta and gamma. Okay, basically what we're going to do, if you want, is that we're going to totalize these dynamics, and yeah, let's consider this exponential. So this intermediate time evolution, this is an intermediate time evolution u1 of t, and yeah, and this it's also maybe easier without here the schedule, right? So the schedule S of t tells us how this S changes in time, and we do is that we assume now a linear schedule. So in the ideal case, we will do right. So at S equal to 0, sorry, at time equal to 0, S is equal to 0, and at time equal to capital T, S is equal to 1, and the Hamiltonian system has been okay, the Hamiltonian system becomes HP. Okay, so the annealing process is just this process in which we change S slowly. In the idea that T is very large. Okay, it must be much larger than the time scale given by the local system. But if we are slow enough, then I tried to convince you the other day, basically the system remains in the ground state and we finish in the ground state of HP. That is the goal of the adiabatic quantum algorithm. Okay? So now let's take this unitary. Let's so I will do a sketchy calculation, so I will not enter into many details because I want to express the idea. But this is one thing that we can do. If you want, I forgot to mention that, okay, here we need to assume that we have a time ordered integral. Okay, so this sum, because of this Hamiltonian tensional commute, no, this sum needs to be performed in time order. And then what we will do basically will be just approximate this schedule by this first function. Okay, we will approximate this. Okay, and what we will do is that we will create p intervals. So we will create p intervals. P intervals such that all the SOP is we have to think about P as a large number, such that the length of its interval will be delta T. It's just the total time divided by P. Okay. So if we do this, then we can understand this as the product for different K's from 1 to P of these evolutions. Let's say S of K times delta for a time delta T at T. And now, of course, so notice that this H of S has these two terms given by this H naught and this HP. And what we will do is basically write explicitly. So one of these exponential. So now what we will do is that we will write this exponential, in particular the Hamiltonian exponential, in its explicit expression, where we see that it has two terms, one term H naught and one term HP. Okay? So if we do that, what we get is one term will be 1 minus S of K delta T. So this is the value of S at time T, okay, that now it has been discretized, times H naught plus another term that will be S of K times delta T times HP, and that's all. Okay? So here, the idea now is just that we apply the Trotter-Suzuki decomposition of this exponential, and we break it up in two exponentials. And we will do only the approximation to first order because we assume that delta T is small enough such that the corrections are negligible. Okay, so basically now we break this into two parts, and assuming that delta T is sufficiently small, and then what we get this quantity times 1 minus S of K of delta T H naught times E minus delta T S S of K times delta T times HP. Okay, so basically the idea here is that, notice that, okay, this will be a number, that can be whatever. This is another number. Let's say this can be a number that we will call beta k. This will be another number that we call it gamma k. And what we see is that we recover that this unitary has been basically broken into a product of pairs of unitaries with the same structure that our U naught and our UP. Okay, so basically what we have just shown is that the quantum approach. Sorry, what we have just shown is that the adiabatic quantum computation is a particular case of the quantum approximate optimization algorithm when the beta case and the gamma case have these expressions here. Okay, so this shows various things. As the adiabatic quantum computation is universal, so if you go slow enough, you can basically generate the ground state of any Hamiltonian. Then also QAOA will be universal. Okay, and this gives the inspiration for. So I guess that the creators of the QAOA algorithm were inspired by the adiabatic quantum computation. Okay, once said that, the advantage of the QAOA is that it's more general. So and therefore, so in general, we currently cannot discretize adiabatic quantum computation and run it in a quantum computer because basically we have the hardware is not mature enough. Okay. Instead, we are able to run shorter programs with shorter circuits where P is not very large, but P is small, and get some results for optimization. Okay, so the idea of QAOA is that it is a valid strategy for having circuits whose depth is smaller and such that they can be run in the current computers. Okay, so in this lecture we have presented the quantum approximate optimization algorithm. We have seen its ansatz, its structure, its possible applications, and finally we have shown that the adiabatic quantum computation algorithms can be understood as a particular case of the quantum approximate optimization algorithm when we take the limit of infinitely many intervals, of infinitely when P tends to infinity, and the betas and the gammas get this particular expression. Okay, this indeed shows that the quantum approximate optimization algorithm is an algorithm that is universal that can generate any ground state, and for this we finish the let's say the series of lectures concerning on the algorithms to solve optimization problems, both in classical and quantum devices. So there is only one lecture left, that is the lecture that will serve as a conclusion, and where we plan to present the current developments in the application of these algorithms and which challenges has the field of quantum optimization in the future.